Okay, the floor is yours, Andre.
Als het goed is, if I'm correct, you're seeing my screen in PowerPoint mode?
Yeah, it's perfect.
Okay, let me also... yes, let me start. So I thought today, so my name is Andre Dekker. I'm a professor of clinical data science in Maastricht UMC University and Maastro Clinic. And I'm also involved in something called the Netherlands AI Coalition. And that's what I wanted to talk about today, a proof of concept in cancer and oncology that we were doing, that we have been doing the last, let's say, 6 months, 9 months for the Dutch AI Coalition. And this is about responsible data sharing between healthcare organizations. And so this is on behalf, if you want, of the building block data sharing. That's a building block within the Dutch AI Coalition and the working group Health and Care. Just for the people that don't know, the Dutch AI Coalition is a public-private partnership in which so companies and the knowledge institutes and societal partners and governments are working together, not just for health, but also for logistic and defense and so forth. And the idea is that the data sharing building block tries to deliver a data sharing infrastructure which is for all sectors. And of course, the working group Health and Care is much focused on getting AI and data sharing done for health and care. And so you can see the obvious relationship between the personal health train and Health Orion, what we do here. So that's why I thought it would be good to update you on what we did there. So the larger goal of the Dutch AI Coalition, especially the data sharing group, is to build this federated data sharing system where data sharing is easy to implement, supported, no vendor lock-in, and international standards. And so there's a picture on the right. An important concept is called international data spaces. This is the architecture that they've chosen. So that's if you want an implementation of the personal health thing, which is different than the one, for instance, from Data Shield or Odyssey/Eden or Vantage 6, which is the Dutch Cancer Registry. So this is another one. And important for the whole concept is that they're looking at multiple application areas, right? So not just health. That's why they also do some different choices. This should result in trusted data sharing, AI, especially for the Netherlands. So there is a Dutch component to it. They also get money from the Growth Fund, about 215 million euros to do this. And of course, you can see the other things here. Now, one of the way the Dutch AI Coalition works is through proof of concept. And there was one proof of concept done in health before we started. And this was mainly led out of Leiden with TNO and other people and the Go Fair Foundation. This was about COVID-19. And their pilot use case had two main aims. So they wanted to standardize data across the country according to the WHO ECRF. So that's a case report form for COVID-19 that the WHO made. So they wanted to make that fair and to be able to query, if you want, across the country for instance, how many COVID patients are there and what's their prognosis and so forth, or the outcome, I should say. So that's data to the algorithm. So getting data out of hospitals to a central location to do something with. The other thing that they did is to do the AI to the data. So this is much more personal health trained style, where data, in this case images, were at the location, and then an AI algorithm is sent to the data. Some things that resonate well with this group: that data sovereignty is key, FAIR principles, and so this is a personal health and implementation based on this international data spaces standards. If you look at that up on the internet, you will find that this is quite a big, especially German Fraunhofer-led infrastructure, if you want. So just to show you some things of the previous proof of concept, here you have 4 hospitals. You can basically send them a Sparkle query, and you get on a patient level some information on those patients. So this is really retrieval of individual data from these hospitals or Castor, which is a ECRF system like RedCap or Open Clinica that you may know. And they did this via TNO was involved in that, making that so there's a consumer that wants data. Basically, you can log into the TNO registry and identity provider, and then you can get the data out of these hospitals. That's approximately how it worked. So you have a consumer which is trusted, and then fair data being sent to this consumer, which then has an algorithm. So data to the algorithm is, sending the data to that consumer. But of course, in personal health, we're looking more at algorithm to data. So then the consumer sends an algorithm to the data. And they also did this, where they could send for instance, an application that could read your handwriting. You can send it to the hospitals where they have some handwriting done. And then back you got information, for instance, on the model accuracy in different sites, right? So the model was, in Leiden, it has an accuracy of whatever 61% and 40% in Maastricht. Well, this is the example that they showed in the previous proof of concept. This is another one where you look at delineating the hippocampus, so brain structure on an MRI. And then classifying it in different sections if you want, and that's also what they showed in the previous proof of concept. You can do this; that you can send an AI to the data. Now, they did this with a number of partners, and then we looked at this proof of concept and said, well, they really used everything in the cloud. So they only used open data. They didn't use real patient data for this. It's really proof of concept where they showed that this works. And really, they didn't do any federated learning of AI. They did mostly federated validation or learning at one side, but not really jointly learning, right? And so we said, well, there's still stuff to do then to look at what do you need to get real patient data in such a federated system, and how do you learn? And that's what the proof of concept for oncology was based on. This was the initial use case. It was changed over time. I'll explain that, but this initial use case where we have brain cancer MRs, and you can delineate the brain. Here is a low grade and a high grade. So you can do, first of all, first question is, where is that tumor, right? So you would delineate the tumor, and then you want to type it, because high grade and low grade have different outcomes and also different treatments that you need. And nowadays this is done with a biopsy, and the idea is that you can do this with an AI, so you don't need to biopsy the brain, which has obvious benefits for patients, right? So they showed, and this is Rotterdam Erasmus work, that they could do this with an with an AI on MR images, deep learning based, with reasonable errors on the curve, so reasonable accuracy. And the question is, can you do this with federated deep learning, right? So this is a deep learning. Is that possible with the IDS solution, which is the animal ASI preferred solution, as I discussed? And what does it take out? What does it take to roll it out in the Netherlands with real patient data? Now, we were faced with a situation that the researcher that was driving this in Erasmus became ill, and ill for a long time. So we couldn't, we had to stop this use case, and we switched to another one, which is very similar, where we looked at CT scans, so different image modalities, not MRIs, but CT scans, and looked at delineation of lung cancer. Right, this is a project that we had on the shelf in Maastricht. But the questions are still the same, right? Is that possible to do with federated deep learning? Could you do with IDS, and what does it take to roll out? So we, as I said, we are looking. There are different personal health and implementation, right? So Janssen, for instance, and Odyssey and Eden, or Honor of Janssen is in that space as Data Shield. I talked about that. The two main ones we're looking at in this project is the one around done by IKNL, so the Dutch Cancer Registry, which is called Vantage 6, and the international data spaces, which was implemented by TNO. In an ideal world, we would like to have all these interoperable with each other, but obviously that's going to take time. But we start at first with those two and look at how different are they and what can we learn from each other, basically. Many partners involved. And what does involvement mean? It means that people were logging into the bi-weekly meetings. Of course, some partners are really active, some were just listening, but that's okay. And there's also some partners there to scale it up, especially KPN was quite active. So KPN, for the non-Dutch people, this is a telecom and infrastructure provider and cloud also in the Netherlands. So they are really looking at, okay, how can we take this and make a service out of it? So that's interesting to hear there as well. So the deliverables we defined is, we want to implement federated deep learning in international data spaces because it wasn't there. We want to do implemented federated deep learning. This should learn, say, in Vantage 6 because also it wasn't there. And we want to do this with real patient data stored within the hospital. So, doing a real POC, if you want, with real live data. And all that, in a legal framework to make sure that this works. So first deliverables implementation of federated deep learning in IDS. So this is mostly TNO's job with some people from Maastro University that did the deep learning itself. So there's a number of changes from in the IDS approach that were forced by basically implementation that we had in health. So the first one is pool-based communications. So IDS initially assumed that you as a hospital would have a server in the DMZ with a public IP that they can reach from the outside. Well, that's a no-go for hospitals. They don't, some don't have a DMZ, but certainly they want to have a server which is publicly available from the internet with patient data on there, right? That's simply from a security standpoint something that they definitely don't like. So they had to change that from a server which can be inside the firewall and just need internet connection. That's what the first basically says. And the second, and I'll explain that later, it's isolating the researcher more. And then they, of course, had to do GPU deployment. They haven't done this in IDS, and then did improve deployment execution. So GPUs are needed for deep learning. This is the setup of IDS. So there's a researcher here that uploads a request, a training request, so a deep learning algorithm to this space here. This is then sent to a trusted compute connector, which sends it to the hospitals. So on the hospitals, there's an XNet, so that's a DICOM, an imaging archive, and a worker. So the app locally learns a deep learning algorithm on the local data. So this could be, for instance, Rotterdam, and the same would happen in Maastricht. And then the local deep learning networks, the weights of the network are shared with the trusted compute connector, and these averages them out and then sends a new learning job to these connectors. And then in an iterative manner, you can basically average, if you want, or look for a globally optimal deep learning model without sharing the data. Here's that aggregation going on. And so what is different in what has been changed in IDS for this POC? So what the TNO did is, first of all, this error was the other way around. So now the hospital initiates the connection to this trusted compute. That's one change. And the other big change is that this trusted compute was never there, right? The researcher was allowed to directly go to these hospital connectors, and now the researcher is isolated. The reason to isolate the researcher is that this communication which happens between the hospital and this trusted compute node, basically that's an iterative thing where weights of deep learning are being shared. And the concern is that if you really look at every iteration and get information on that, you can reconstruct some of the data inside this hospital. And so there's a privacy concern there, and that's why it was isolated, right? That's why the communication can only be done through those two, through this compute connector. So that's those are two main differences. The way this looks at in IDS is the following. So here's the picture again. The researcher can just upload something. Here's the worker ID. Those are the hospitals, Erasmus and Maastro. These are some considerations of deep learning that you see, some meta parameters. And then you can choose a model and you can start the federated learning. So you generally start with a model which you then adapt based on the data, in this case of Maastricht and Rotterdam. And you can see here the iterations happening and the loss and the dice. So the dice is typically a metric that we use to compare the quality of a segmentation versus the AI-based versus human-based. So you want to have the dice to be low. And then iteratively, it starts looking for the deep learning network, which has the lowest dice and the lowest loss. So that's what's happening. You can see a few rounds here. I think there are 5 rounds with 40 iterations. And in the end, you get the deep learning network. You can download that. That's the idea. Oh, now I have to press escape.
Andre, 2 questions. So were you able to compare it to the centralized learning? Was that an option here? And the second question is, you mentioned as a way to aggregate the results from the 2 different sites and average. Is that always needs to be an average, or can that be an alternative way of aggregating?
So that can be an alternative way of aggregating. To answer your last question, right? There are different ways to do federated deep learning. Averaging is kind of the no-brainer, the stupid one, if you want. One a little bit better is to do this weighted on, for instance, on the number of patients that each has, as an example. But there are also much more sophisticated ways of doing this. Really doing some back propagation as well inside the central server. So there are different options there. To answer your first question, in this IDS implementation, we didn't do this, but it is in principle possible. This implementation to do it, because we only used open data still here in IDS. So this was all based in the Tino cloud. And so you could compare federated with centralized deep learning. This has, by the way, been done many times, and consistently everyone finds that there's no real difference between federated and non-federated deep learning in terms of accuracy of the model. Of course, the deep learning itself may be different, but you don't even know because it's such a complex system. But of course, in what I will show next is the one in Vantage where we use real patient data. There you cannot compare the two. But we do know that federated learning is then becoming better than centralized learning, because the federated learning algorithm sees more data than the centralized learning, because you can't centralize. Hopefully that answers your questions, Peter.
Yes, perfect. Thank you.
So
I also have a question, if I may.
Yeah, sure.
My question is the weights that are communicated.
Mm-hmm.
How sensitive are they?
Yeah. So there's a there's an active research area. So we're talking about these. You can talk about 2 different weights. You can talk about these weights, which comes from the individual hospitals, right? That are every iterations, there's weights coming back and forth. And you can talk about the final weights, if you want, that gets sent back to the researcher. There is an active. So let me. If you learn a very, very deep network, right? You're basically learning a network which can recreate your training data. This is something, at least, that people think is possible. For images, it has never been completely proven, in the sense that you can use a deep learning app, for instance, to regenerate a CT scan, but that's or a face of a person, right? But that face of a person is, it looks like a real person, right? It's very similar to the persons inside the database, but it's not that person, right? It's a similar person. So, but of course, if you become very similar, then you maybe recognize someone. So there are a few. So the short answer is yes. This is sensitive data. This was one of the reasons to split the researcher through this trust compute connector, so the researcher doesn't have access to these iterations, which may, in an attack, learn something about the hospital connector or about the hospital data. The other thing that we're looking at is in this line, add some noise, so that the final model that the researcher gets is not cannot be used to reconstruct original data. Does that answer your question, Russell?
The question was from Thijs, but
oh, sorry. Sorry. See who's asking the question.
Yeah, that's true. But it answers my question. But it would be interesting to really quantify the leakage, if that's possible. And
yeah, it's not. It's not. That's the problem with deep learning.
Yeah.
It's very, very. It's. But there's a whole bunch of literature. Because to be honest, this is not different between centralized or federated learning, right? also when you have a centralized data set, you can learn such a deep network that you can reconstruct.
Yeah, but if it's centralized, you have all the data by yourself, then you don't really have a problem.
Well, not really. I mean, if the researcher, so suppose this is a trusted, suppose CBS.
Only the eventual outcome of the learning network.
Right. So the eventual outcome, if that's too deep, then that's a concern. But it's also a concern if you get access to these intermediate ones, right? So both are a concern. So the intermediate ones are hidden, they cannot be accessed, and the central one the researcher gets back is similar to a centralized situation. But there's plenty of work being done on that to understand what's the risks there.
Yeah. Thanks.
Okay. Yeah, so that went quite well. Some discussion about this was all deployed in the cloud, as I said. What CPU, GPU, what storage backend to make this work. But this is, let's say, bread and butter engineering work.
And Marco, is there also questions from your side?
Well, I had a question. I thought maybe I should wait, but I had.
I thought I saw a hand, but maybe that was the other.
No, I didn't put up a hand, but okay. Now that I'm speaking anyway, I was wondering about the process flow that you described in the beginning of the previous slide. I didn't completely understand it, but it was because I was thinking of if this was similar or identical to the Hadoop-based way of distributed programming with job trackers and so on. Is that how? Because I was wondering how the hospitals, the individual hospitals, know what they are going to compute.
It's a good question. This is a Kubernetes-based system, IDS. But I don't know enough of technology to compare that to a Hadoop one, to be honest. And also because this was all in the cloud, we haven't really looked at what the hospital sees or doesn't see. So I don't know, is the honest answer. In the IDS solution. I will show you now the Vantage solution, which is which was changed as well. So what was changed there is the also in the Vantage solution, we decided to introduce this. You can't see my. Well, let me change my pointer that I can point at something. Yeah. Yeah. Also in the Vantage solution, we introduced this trusted compute node for the same reason as IDS. We actually did this before IDS, so it's in time it's the other way around. Again, to separate the researcher from the intermediate weights that are being shared between the centers. And what you will and what's also different between the Vantage 6 solution and the IDS solution that I just showed is this was made with real patient data. So with patients, with once these two servers are sitting in the Azure cloud, Vantage 6 where the researcher logs in, and this trusted compute node, but these are actually inside Maastro, these two. And so you do go over the internet, and so you will see much slower. What you also see is this is much more command line based work than the nice interface that IDS has. But also it gives you a little bit of an idea what the hospitals see and what is happening on the site.
We are going to show a demonstration of federated deep learning using Vantage 6 infrastructure.
Let me check if you can hear Ananya's voice.
Yes, we hear it.
Okay.
Execution, let's just have an overview of the infrastructure itself. Any federated machine learning task in Vantage 6 is orchestrated by a central server. A researcher sends a request to the server to send a task to the data nodes. The data nodes contain the data where the model needs to train locally. Upon the researcher's request, the Vantage 6 server sends a request to all the data nodes to download a Docker image. This Docker image runs locally, trains the model on the local data, and sends the model back to the server. The researcher extracts these intermediate models from all the data nodes that is in the server, fetches them, aggregates it to compute a aggregated model, and sends the model back to the data nodes. This process continues until we achieve convergence or we reach the end of our number of iterations. However, this scenario has been slightly modified, and we have included a trusted compute node. This is to ensure that the intermediate model, instead of reaching to the server, now reaches to the trusted compute node. For all the n number of iterations, the data nodes sends the model to the trusted compute node. The trusted compute node collects the intermediate models from the data nodes, computes the aggregated model, sends it back, and this process is carried over until we reach convergence or we reach n number of iterations. The final aggregated model is now sent by the trusted compute node to the Vantage 6 server, and the researcher can only fetch the final aggregated model. This has been done in order to prevent the researcher from reaching to the intermediate results or the intermediate model. Now let's go to the execution. The first task that the researcher does is to authenticate itself to a Vantage 6 server. In addition, all the communications that goes on while execution of the task, the communications are end-to-end encrypted between the data nodes and the master node and the server and the researcher. We have previously registered a researcher with the server. The first task we will do is to authenticate that researcher with the server. We have hosted a central server in this location, which is basically this server you can see here. So let's try to authenticate the user first. The user has been successfully authenticated. The user then retrieves the desired collaboration from the server to which it needs to send the tasks to. The collaboration hosts all the information about the organizations and the nodes that are associated to a particular project or a consortium. As we can see here, we have 3 nodes. One of them is the master node, which we have configured slightly differently than the data nodes. The other 2 nodes are essentially the data nodes hosting the data. The master node itself does not contain any data, but only hosts the aggregated part of the algorithm. Once the researcher has authenticated itself, the next task is to describe the task that is intended to send and create that master task. As we can see here, we have defined certain inputs which contains organization IDs, which are 2 and 17. As we can see from the collaboration, we have 2 data nodes for this execution purpose and a master node. The master node is basically defined by this. Also, in addition, we have 3 nodes running in background. One of them is the master node. As you see on the upper side of the screen, the other 2 nodes are the data nodes. Now let's try to send a task to all the nodes. We have containerized the algorithm in a Docker image and hosted it in Docker Hub. And we specify the name of the image in this section of the task. The method client.task.create creates the task and also posts the task to the server. Now, let's look what happens at the master node side. So we see a new task has been added, which is task 478. It runs a Docker image. Similarly, in some time, the data nodes too will receive the subtasks that the master node will send to. Let's just wait for some time. While the master node and the data node runs the algorithm in the background, let's again go back to the infrastructure and see what's exactly is happening. So we have modified the infrastructure, the node part of the infrastructure, by including a REST API. The REST API generates a JWT token. That JWT token, along with the task, is sent to the server. Now, within the algorithm part of the container that runs in the data nodes, instead of sending the task to the server, we now know from our environment variables that there is another node called the trusted compute node sitting intermediate between the server and the data nodes, which hosts a REST API. Now, any moment the node completes a iteration, the model is posted to this REST API. Now, this REST API authenticates the model if it's from a trusted source or not by authenticating the JWT token. And this process continues for n number of iterations. Once when the subtasks are completed, the trusted compute node sends the results back to the server. Now let's go back again and see what's happening in the master node. As we see here, certain number of iterations are going on. As we see in the data nodes, certain number of iterations are going on here as well. So we need to wait for some time until the complete execution is done. So from the master node's prompt, we see that a result ID has been sent to the server. Now let's go back to the notebook and see what we get in the result. So we fetch a lot of things. Let's just filter out only the result part. So our model has been trained, aggregated, and the final aggregated model results we can see here. Our deep learning algorithm actually does a gross tumor volume segmentation from CT lung images. So we obtain a loss and dice coefficients for our training purpose. We obtain the training loss, training dice coefficient, validation loss, and validation dice coefficient. We also see that the number of iterations that went on and completed is 4. Also to mention that the algorithm is trained on 37 patients. 35 of the patients are private data from Maastro. 2 of the patients are public data. And this data has been split into 2 nodes, and we have successfully trained the model. So our experience about developing this algorithm and the infrastructure. So we successfully have seen and demonstrated that federated deep learning with Vantage 6 is possible. Introduction of a third compute node in between has successfully prevented us from having the intermediate results in the server. We have tested the infrastructure by scaling it up with at least 9 real centers, and the infrastructure is stable. The integration of the federated algorithm with the infrastructure has fairly been easy. However, we have still some improvements to do. So as I mentioned earlier, we generate a JWT token. For our n number of iterations, as of now, the JWT token is constant. Our future improvement includes refreshing the JWT token for each purpose, each iterations. There, we still need to send certain intermediate messages to the server so the researcher understands from his end which iterations has been completed and if there is any failure scenario, or he can have some logs from the data nodes. Abort and fail scenario has not yet been handled, which is part of the future improvement. In case of one of the nodes aborting or failing or going off, for a real-life federated deep learning algorithm for n number of iterations, it would be incredibly difficult or time-consuming to train it from the scratch. In that scenario, we aim to extract the last aggregated weight at, let's say, k number of iteration, and in the next execution, feed the algorithm with the last aggregated weight as the initial weight algorithm.
Okay, so that's, as you can see, a very a more technical implementation. And I like to stress that the difficulty here is that these data nodes are really inside hospitals, right? So when Ananya was talking about the 9 centers, this is 9 centers globally, right? In China and in Brazil and Australia and in the Netherlands and so forth. And so getting that communication done and working with all those different environments is actually quite challenging. And this is what we did in the Vantage 6 solution. So the question is still, if in the IDS solution, how easy will it be to deploy inside the local hospitals? On the other hand, the IDS solution, as you can see, is quite mature as well. So and it's very similar in its approach in the end.
Can I make a remark?
Yep.
If I see trusted computing node, I always get a bit itchy. And so apparently there's a trust problem, and they solved it by creating an extra node and calling it trusted. And then I wonder, why is it trusted? Who manages that node? And why does this node does not collude with other parties? I mean, yeah.
Yeah. Well, what do you call it? Trusted or secure? I mean, the whole idea was to separate the compute from the researcher, right? That was the whole idea. It is not that we feel that there's identifiable information on that secure compute node, but you are basically doing, from a security perspective, cutting down another attack factor, which is the rogue researcher. So that's what you're doing. Of course, you have a different. Then if you don't trust the researcher, you have to trust the entity that gives you this compute node, right?
Yeah.
Yourself to.
Who manages this compute node?
Yeah, well, that is a third party that does that for you in the Vantage 6 and in the IDS solution, right? In both cases, it's a third party that hosts that. But of course, then you can start looking at, okay, if I don't trust that party, how can I then ensure things there? And then you look at maybe homomorphic encryption or SMPC as additional security things added to it if you don't trust that third node. Yeah.
Yeah, I understand the problem. So
yeah,
it's
always there is aggregation needing go on, and that has to happen somewhere. So that's always going to be outside the individual data nodes, or one of the data nodes could be, of course, a trusted party as well. Okay, so to finish up, we're also looking at the.
Can I follow up on that? On that, because I maybe there's something we can do with the comment of Thijs, is that in the pictures that we show, we make it more clear who is seeing what. Because I think for me that's the main point. So just the word trusted doesn't really convey that information, right? So it's also because in this case, I think the idea is that the researcher doesn't see what's on the trusted server, if I understood you correctly. That's actually the point. So and also sometimes in our personal health train and fair, it's that a human being doesn't see certain data, right? But we don't really make that explicit in our picture. We just call it trusted. But so maybe it's useful to think about if we can actually make that explicit in our pictures. This person sees that person sees that, this agent sees that, no person sees it.
Right.
This type of information, rather than just security, because that's in a way an issue in itself, right? That's about hackers who whether they can get into your system or not.
Right.
But who sees what?
Yeah.
People just want to do the right thing, right? That's maybe valuable too.
Yeah, no, true. The terminology matters here, right? So if you want what we call the secure server, what was called a secure server in this picture, we typically would call the master node before, right? So the master node, what it does, it sees the intermediate results from all the data nodes and try to make an average out of that, for instance, right? Or aggregates the different results and then iteratively sends it back. So this server sees intermediate results, right? They're still anonymous, right? But they're intermediate results. And the researcher only sees the final result, right? The final model. So that is what is. But you're right. You can make this more explicit, I guess. Yeah. Another way of dealing with those problems is also by not just focusing on technology, but also focusing on legal. And that's the final piece of the POC. So we use real data from real patient. This has obviously some sensitivities. And we did define a contractual setup. And I guess related to what we just discussed, this contractual setup and the way to do it is really dependent on the technology used. And where the data flows and who sees what as was just discussed. We should also say that federated learning is something that isn't covered by the law as such, right? So we do have to sometimes do a little bit of trailblazing. The experience is that the contractual stuff is way more important than the technical stuff, typically taking us 1 year to get done rather than the tech. And this is deliverable of the POC as well. So there are two main agreements, and this a little bit answers the trust question. So there's the concept of the personal health thing. There is a party, a third party, which you perhaps somewhat trust, that delivers the infrastructure. And the infrastructure meaning they deliver the secure compute node, and they deliver the interface to the researcher. So the researcher is over here. So they are trains, and these are the stations that are kind of different setups. The idea is that only anonymous data is being sent across the track in these iterations, and also only anonymous data is being sent in the final iteration from the track to the researcher over here. And so for this, you need an infrastructure use agreement, which is a bilateral agreement between the track and the train, and between the track and the stations. And basically, what you're saying is that this you shall not put in a virus, you shall not steal patient data, you shall only put anonymous data on the track. And that's so sometimes I think focus too much on technical, but you can also embed trust and legal agreements, right? So that's the first agreement that we set up, and that is now available. The second one is the consortium agreement. The consortium agreement is a bit more complicated, because in the consortium agreement, you have this problem that the researcher is the controller in GDPR sense. So they are determining the reason for data processing, and that makes them a controller. So they want to have an answer on that question, right? And so that makes them a controller. But the weird thing that the controller doesn't control the data, right? Because the controller can't see the data. This is in these data spaces or in these stations. And so we had to set up an agreement where these stations become either data processors for this controller, or these stations become a joint controller with this controller. This is all GDPR speak, but we managed to get this done. And in this consortium agreement, you're dealing again with GDPR stuff, but also with things like IP, authorship, who gets the algorithm and things like that. And of course, what exact data elements do you need to put in the station for this whole project to work? So that was done. So infrastructure use agreement, consortium agreement. We had 6 hospitals in the Netherlands approving this, signing it, approving it. And international, we have 15 hospitals approving it. So these are some countries that are now signing this agreement, that have signed the agreement. So that means that the agreement is quite stable. And also we have shared these agreements with the LC Server Desk Health RI, so that people that want to start their own personal health network and that need contracts can look at this and perhaps reuse it as well. That's it. So next steps. So of course, a white paper, scientific paper presentations, continuing the synchronization. Some interest from international partners. We are setting up an ELSA lab to look further at this privacy issue. And some new POCs are in the making, or at least some ideas are in the Touch AI coalition to look more at vertical partitions. So the problem of having a slice of data in CVS and a slice of data in the hospital, and rare diseases. And the reason to do these POCs is that the legal agreements that we have until now don't cover this yet, these use cases, because in rare diseases you can question whether or not only anonymous data goes across the line. In the vertical partitions, that's certainly not the case. So some new POCs needed, perhaps. This is
André?
Yep.
Can you, for me, elaborate a little bit on the rare diseases? With whom are you doing that?
But we're not doing that. We're just seeing that this needs to be done, right? So these
Okay.
are more, things that we haven't covered in this POC yet.
I'm very much looking forward to it. Then.
Yeah, well, we don't.
André.
This is also up to everyone to just go to Dutch AI Coalition and submit projects, right? They have 188 million will release through a grant system likely. And so these are two things that you might get into. This POC that I just described and the previous POC were unpaid, right? This is just us being interested in doing this stuff. But these new POCs will probably go through a grant mechanism, so everyone can subscribe to those.
Okay, we'll definitely look into it. One of the things I was thinking of, André, is that I think some of our leading people in the rare disease community that we work with, like Anna Raad, should learn from you. So
right.
if you would open to that, I will see if perhaps we can have a short meeting at least with her,
right,
to see what is possible. I think that will lead to some eye openers.
Yeah. Okay, definitely. So that's it. So many people have worked on this, obviously, all for free. As I said, this is unfunded research, so that makes it also a bit special that we actually got so far. For me, one of the learnings was, besides having these agreements done, which took some time, also that you see when you start having two infrastructures, like in this case IDS and Vantage, working together, then very quickly you see convergence on the way we should do things, and that's I think also an interesting conclusion that I have. So that's it. Thanks.
Okay, thank you, André. That was very, very interesting. Are there any more questions?
I had one on the chat from previously. If for this discussion on the centralized versus federated, if there are papers we can refer to, and if not, if we should consider adding something to the.
No, don't add something. This has been researched many times. So just the literature is there.
Yeah, can you provide maybe your favorite papers because this question comes up again and again and again. I was in a rare disease meeting the last 2 days, and again this question came up. So I think it's good to.
So the question is, of course, that people that you share a paper for deep learning said, no, yeah, we don't do deep learning, we do Bayesian networks, and then so it depends on the algorithm how you need to federate this. That's the issue. So if you can supply me with the algorithm that they're using, like a Cox or whatever, I can supply you with, this has been done in a federated sense.
And that would be, I'm thinking that could also be useful if we have a sort of table of with these kind of methods, go for federated, no problem. For these, maybe take a second look, this kind of thing. Yeah. Also, because I think also in your previous talk that you gave in this session, André, for me, that was also important because it showed that you do, in a way, very basic algorithms. People think with machine learning that it's always something sort of moon rocket science or whatever, but it was actually quite basic statistics that it gets the power from doing it on a lot of nodes, right? And that's, I think, also it's useful for people to see what methods are all applicable to this, and would all fall under the category of federated learning.
Yeah.
Would those papers have that as well, or would that be something we would have to create? This table of?
No, I don't think that's a table. I think these are individual papers that have described this. We have done this for deep learning. We've done this for support vector machine. We've done it for logistic questions. We've done this for statistical Cox models, right? I don't think there's an overview. I was just looking at. There's one European project that simply provides all these federated, so that has federated all these algorithms, right? So that at least there's tooling there to federate them. Whether or not that compares between centralized or not is another question, I guess.
We have 2 more questions, but we have also 5 minutes left only. What shall we do, André? Would you like to answer these 2 questions, or would you like to say a few more words on the PHT and how we are going to go to the next phase of PHT?
Let's keep a minute at the end, because I think it can be very short to update. So we'll have 1 question or 2. Let's try.
Okay, 2 questions. Marco first. Marco Spruit.
Yeah, okay, André, great presentation, very interesting. But one of the earliest first slides, you showed the landscape of federated learning solutions.
Mm-hmm.
So what is the common denominator? So how are they different, and do they all use REST APIs, all virtual machines to communicate? So can you say a little bit about the diversity in the solution space, and why you use Vantage 6, for example?
Right, so the first diversity is about what type of data are in those stations, right? For instance, the one that Janssen and Odyssey are doing is very much clinical and observational database with text data that is in an OMOP database, and where they use mostly, I think, R scripts to federate across those different sites. So there's that space. So there's differences in databases. Do you use OMOP or OPAL or RDF or FAIR, right? And what does that exactly mean? So there's a change there. Then there's a change of delivering your algorithm to the node. So that can be Docker or Kubernetes or R scripts, or we did MATLAB in the past. And then there is a way that then there are differences in aggregations, the way people do this, right? So some people put a joint in a centralized secretly the data and do the calculation there in a whole secure environment. Other people do real federation, so you need this split of algorithms. So there is a change, but as I said, the interesting part for me was that when you start working together, you can see that you're quickly reusing each other's architecture to a large extent. Yeah.
Okay. Then Thijs.
Yeah, thank you, André. Nice presentation. Interesting. Also to see the collaboration with IDS and data sharing structures. My remark was, if you consider making machine learning algorithms federated, it really much depends on what kind of algorithm you're talking about, as you mentioned. But what also matters is how is the data distributed? And in particularly, is it horizontally or vertically distributed?
Mm-hmm.
And yeah, well, my question is, in your example, is it horizontally or vertically? I guess the first one, but I'm not sure.
Yes, it's horizontal, right? And it assumes, because that's our main use case, that we have hospitals in the world that have complete data that we want to learn from, but we don't have overlapping patients.
Yeah.
The vertical partition, we talked about this last time from, what's her name again from TNO?
Maribeth?
Maribeth.
Van Egmond, yeah.
Yeah, that talked about, how to get the intersection between two vertical partitions, for instance.
Yeah.
Use MPC and encryption to do that. Yeah. That's a separate use case. Yeah.
Okay, thanks.
Okay, given times, I'll guess we can stop recording. I'll switch to Dutch. I can talk